Hello and welcome to this presentation. Today I am going to be talking about the Fermi Gamma Ray Telescope and the discovery of the Fermi bubbles. First, a brief overview. These are the topics I'm going to be talking about. Firstly, I will discuss the Fermi Gamma Ray Telescope, its instruments on board, its mission objectives, notable results, the Gamma Ray Sky Map especially, and then I'm going to be talking about the Fermi bubbles. The Fermi Gamma Ray Telescope was launched on 11 June 2008. It is a joint NASA and US Department of Energy project with contributions from several institutions in France, Germany, Japan, Italy, and Sweden. It studies the cosmos in the energy range of 8 kiloelectron volts to 300 gigaelectron volts. Fermi Observatory is actually successor to the Compton Gamma Ray Observatory, and the main instrument on Fermi, called the Large Area Telescope, is actually the successor to the EGRET or Energetic Gamma Ray Telescope aboard the Compton Gamma Ray Observatory. So these are the instruments on board. The main payload consists of the Large Area Telescope or LAT, and the secondary instrument is the Gamma Ray Burst Monitor or GBM. This figure over here shows the positioning of the instruments on the Fermi Observatory. The Large Area Telescope sits on top, and the several components of the Gamma Ray Burst Monitor or GBM are located across the various parts of the satellite. The Large Area Telescope or the LAT is the main payload aboard the Fermi Gamma Ray Observatory. It makes observations through the process of pair production. Incident photon directions are detected by reconstructing the trajectories of the electrons and the positrons that are produced in this pair production process. The baseline LAT is modular, consisting of a 4 by 4 array of identical towers. Each 40 by 40 cm square tower comprises of a tracker, calorimeter, and data acquisition module. When the pair production happens, the calorimeter walls produce an electron shower that is detected by the detectors. This implies that a positive reading in the LAT would consist of an electron shower and two particles, one positron, one electron, appearing to come out of one single point. This point is the point of the pair production that I am indicating here in this figure. The gamma ray burst monitor or the GBM includes two sets of detectors, 12 sodium iodide scintillators, each 12.7 cm in diameter by 12.7 cm thick. They cover the lower energy range from a few kiloelectron volts to about 1 million electron volts. The GBM provides burst triggers and locations. So this is more like a rapid action instrument, and it can see the whole sky in at any given point of time. The whole sky except the sky portion of the sky covered by the earth, and it is basically used to detect and immediately calculate the position of any transient event like a gamma ray burst. It also consists of two cylindrical bismuth germanate scintillators. They are also 12.7 cm in diameter by 12.7 cm in height. They cover the range of 150 kiloelectron volts to about 30 million electron volts. So the NAI detectors and the BGO detectors nicely overlap in a range to provide more robust readings. These are the main mission objectives of the Fermi Observatory. Fermi was basically built to observe processes that involve high energy astrophysics, and since these are the exotic systems that produce gamma rays, these so the mission objectives include to explore the most extreme environments in the universe where nature harnesses energies far beyond anything possible on earth, to search for signs of new laws of physics, to explain how black holes accelerate immense jets of material to nearly light speed, to help crack the mysteries of powerful explosions that are known as gamma ray bursts, and to answer long standing questions across a broad range of topics, including solar flares, pulsars, and the origin of cosmic rays. These are some of the notable results that have been obtained from the Fermi telescope. It detected the gamma ray burst GRB 13427A, that is the most powerful gamma ray burst ever detected. In 2013, LAT provided proof that supernova shock waves are at least one of the processes that produce cosmic rays. This was an idea that was first introduced in 1949 by the Italian American physicist Enrico Fermi, after whom this observatory was named. It discovered the Fermi bubbles. These are bubble like structures that extend from our galaxy, and I will talk about them more in upcoming slides. It also observed GRB from the merger of two neutron stars in 2017, that was also the source of a gravitational wave that was detected by LIGO. This was the first instance when light and gravitational wave were simultaneously detected from a single source. The Fermi telescope also produced the gamma ray sky map. It confirmed Einstein's idea that the spacetime is smooth and continuous, and disproved theories of a lumpy spacetime proposed by many new theories that are trying to um, coincide the worlds of quantum mechanics and general relativity. It also discovered the first gamma ray pulsar. This is the famous gamma ray sky map. One of these was also made by CGRO, or Compton Gamma Ray Observatory, and then of course the latest one is made by Fermi. I'm going to show you two images, and they will demonstrate the improvement in resolution of gamma ray observations in the 25 or so years between the launch of CGRO and the time Fermi made this gamma ray sky map. So this is the map that was made by CGRO's EGRET, and this is the map that was made by Fermi. You can see even at a glance that the resolution of the map made by Fermi is much better than the one made by EGRET. And then of course Fermi bubbles. This gamma ray sky map that I showed you earlier is actually the map that was the reason behind the discovery of Fermi bubbles in the first place. Fermi bubbles are two giant bubble-like structures that spread out from the center of the galaxy in both up and down direction, or northern and southern directions. The edges of Fermi bubbles was first observed in X-ray by an observatory called Rosat, which is basically a German-based observatory. So this blue area that you can see was indicates the X-ray observations, and this whole magenta or pink area that you see is the gamma ray observation. And as you can see, this is the plane of the galaxy, and compared to the plane of the galaxy, the Fermi bubbles are humongous, and their entire structure is visible only in gamma ray. This whole stretch from end to end is actually 50,000 light years. This map labels all the structures in this picture. So these are the X-ray emissions, gamma ray emissions, the position of the sun over here, and the Milky Way galaxy, of course. These are the possible explanations that have been given to explain the presence of Fermi bubbles. So at the time of the discovery, we knew that emissions from the bubble are much more energetic than the gamma ray fog. They are actually in the giga electron volt range. The bubbles have well-defined edges, which implies that the structures were formed from large and rapid energy release, which is why you will not see any diffusion near the galactic center or near the point of origin. Two possible explanations were given to explain the presence of these structures. One of the theories states the star formation as the cause of the Fermi bubbles, and the another states the cause to be the black hole activity. The star formation theory simply says that intense star formation in about 700 light years around the galactic center led to the formation of these bubbles. Radio polarization revealed that these bubbles have relatively strong magnetic fields, which are expected from star formation theory, and there were spiraling ridges observed in 2012 that suggest fluctuations in the history of star formation over the past a few million years or so. The black hole activity theory simply states that the Fermi bubbles were the result of black hole outflows from the black hole at the galactic center, which is Sagittarius A star. This artist's concept shows how black holes may also cause the spiral ridges. As we have seen from other galaxies, black holes obviously cause incredibly powerful jet outflows from their accretion disks. Hubble in 2017 studied the spectroscopic data from Fermi bubbles. Astronomers used the cosmic origin spectrograph or COS aboard the Hubble to construct UV spectroscopy of radiation from 47 quasars passing through the northern bubble. So the light of the quasars that passed through the bubbles, as you can see in this figure, was observed. So this is the ray that is arriving from these quasars, and here is the sun, and we are making observations of the absorption lines that appear due to the presence of the Fermi bubbles. This was controlled by observing several other quasars that did not pass through the Fermi bubbles, and it was found that only the quasars whose radiation passed through the Fermi bubbles showed a significant blue shift, whereas the quasars whose radiation did not pass through the Fermi bubbles did not show a blue shift. This spectroscopy also revealed that the composition of the bubbles consists mainly of carbon and silicon, and the temperature of the bubbles is about 10,000 degrees Celsius, which is actually quite low because temperature of plasmas or gas outflows of this nature is usually millions of degrees Celsius. This spectroscopy also revealed that the particles inside the Fermi bubbles travel at thousands of kilometer per second speeds, and the bubbles have approximately 2 million solar masses in them. Also, these bubbles are estimated to be about 6 million years old, which is when astronomers estimate that there was a huge inflow of interstellar or stellar matter into the supermassive black hole at the center, and the black hole released this jet outflow that caused the Fermi bubble. This is basically all we know about Fermi bubbles so far. It is a relatively recent discovery, so it is definitely a very interesting and very active area of research, and we will have to see what comes up in future studies and observations of this particular phenomena. So that is all for this presentation. These are the references, and I thank you for your time.